Hello, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. And in the session today, we are going to discuss on particle spin and Stern-Gerlach experiment. As we know that when a particle is taking rotation on an orbit, then its angular momentum is perpendicular to the plane of that orbit, and this is what is shown by this diagram over here. And this is given by L is equal to R cross P. Now, classically, there is no restriction on the magnitude or direction of the orbital angular momentum. From a classical point of view, an electron carries a charge, and therefore, its orbital motion will give us a current loop, and that will subsequently produce a dipole magnetic field. The magnetic field, this magnetic moment of this tiny magnet will be given by mu L equals to Q by twice M into L. Now, in the same way, if we consider the spin angular momentum, that is the bodies rotating about their own axis, then the spin angular momentum will be there, and it will be given by S is equal to I omega, where I is the moment of inertia, omega is the angular velocity. And if this sphere also possesses an electric charge, then the circulation of the charge around the axis of rotation will constitute a current, and hence this will give rise to a magnetic field given by a similar expression as we have seen in the orbital momentum. So this is also given by mu s is equal to Q by twice M into spin angular momentum. Now, wave mechanics in general and wave function in particular, they describe the properties of a particle moving through space, giving information on its position, momentum, energy. That is, all the information about the particle is given by its wave function in wave mechanics. Now, wave mechanics also provides a quantum description of the orbital angular momentum of a particle, such as that associated with an electron moving in an orbit around an atomic nucleus. The magnitude of the angular momentum is limited to the value because it is quantized. So it is L is equal to a square root of L plus 1, where L is equal to 1 to 3, etc. Now, if a special relativity and quantum mechanics are combined, it is observed that even if a particle has zero orbital angular momentum, its total angular momentum is not zero. Now, this angular momentum is due to the intrinsic spin of the particle. The possible values for the magnitude S of the spin angular momentum turns out to be in the similar way as in the orbital one. S is equal to square root S into S plus 1. But with a significant difference of appearance of half integer values for a spin quantum number S. Now, there is one classical property, however. We have seen that there is a complete change when we go from the classical to the quantum, but there is one classical property of angular momentum that does carry over to the quantum mechanics. Now, if the particle is charged and if it possesses either orbital or a spin angular momentum, then there arises a dipole magnetic moment. For electron, the dipole moment is given by mu s is equal to E upon twice me g into s. Here, me and E are the mass and charge of the electron, s is the spin angular momentum of the electron, and g is the gyromagnetic ratio. Now, this is classically equal to 1, but is known to be equal to 2 for an electron. Now, Stern-Gerlach experiment, now we come on to. Mind it, this experiment was done in 1922, whereas the idea of a spin by Uhlenberg and Gaudsmit came in 1925. So when this experiment was being done in 1922, there was no idea about the spin existing. There was not at all. The original experiment, therefore, had nothing to do with the discovery that electron possessed a spin. This experiment intended only to test a space quantization associated with the orbital angular momentum of the atomic electrons. That's all. Now, predictions made by old quantum theory developed out of Bohr's work was that the spatial component of angular momentum could only take discrete values. That is, the angular momentum was spatially also quantized, so that the direction of angular momentum vector was restricted to only a limited number of possibilities. Now, this could be tested on the simple principle that an orbiting electron gives rise to a magnetic moment proportional to the orbital angular momentum of the electron. So by measuring the magnetic moment of an atom, it should be possible to determine whether or not a space quantization existed. Now, results of this experiment were in agreement with the prediction. However, existence of electron spin was not suspected at all. Later it was realized that the interpretation of results were incorrect and that the experiment was direct evidence that electrons possessed spin. This is experimental arrangement. As you can see that a collimated beam of silver atoms heading in, say, y direction and passing through a non-uniform magnetic field is directed along, this magnetic field is directed along z-axis. This magnetic field is non-uniform. This is the screen on which these deflected silver atoms will be striking at. So this is the experimental arrangement. Now here we have to take care that the magnetic field is pointing along z-axis, whereas the silver atoms are moving along y-axis. Now, assuming that the silver atom has non-zero magnetic moment mu, the magnetic field will have two effects. Number one, magnetic field will exert a torque on magnetic dipole so that the magnetic moment vector will precess about the direction of magnetic field. This will not affect z component of mu. Number two, non-uniformity of the field will mean that the atoms experience a sideways force given by Fz is equal to minus delta U delta Z. Here U is equal to minus mu dot B, this potential energy, is equal to minus mu Z into B, because the angle between mu Z and B is 0, and for other components it is 90 degrees. So this sideways force Fz will be given by Fz is equal to mu Z minus mu Z delta B delta Z. Now let us consider the deflection. Classical physics predicts that due to thermal randomization in open, the magnetic dipole moment vector of the atoms will be randomly oriented in space. This will lead to a continuous spread in the Z component of the magnetic moments of the silver atoms as they emerge from the oven, ranging from minus mu Z to plus mu Z. Now, different values of mu Z will lead to different values of forces acting on the atoms depending on the magnitude of mu Z, as we have seen the formula for Fz. As expected, a line should then appear on the screen along the Z direction. But to the contrary, the silver atoms arrived on the screen at 2 points corresponding to the magnetic moment mu Z. This mu Z is plus minus mu B, where mu B is known as the Bohr magneton. Now this is the figure for deflection of the silver atoms on the screen. Now Z is equal to half AT square, A is equal to F upon M, and F is given by, as we have seen, that was mu B delta Z. So here we can see this deflection Z is proportional to the spin and to the magnitude of the magnetic field gradient, that is delta B delta Z, and it is inversely proportional to the kinetic energy. Now, thus, space quantization was confirmed by this experiment in no uncertain terms. However, the full significance of the result was not realized until some time later, after the proposal by Uhlenbeck and Goudsmit that electron possessed intrinsic spin. Now, the full explanation based on what is now known about the structure of the silver atom is as follows. That is how we understand it. Silver atom has 47 electrons surrounding the nucleus. 46 of them form a closed inner core of total angular momentum 0, and the electrons with opposite spins pair off, so the total angular momentum is 0. Thus, there is no contribution to the magnetic moment due to the core of the silver atom. the 47th electron also has zero orbital angular momentum. So the only source of any magnetic moment is that due to the intrinsic spin of the 47th electron. In this way, the experiment represents a direct measurement of one component of the spin of the electron, the z direction in the present experiment. Now, there are two possible values of Sz corresponding to two spots on the observation screen, as required by the fact that S is equal to half for electron. That is, they are spin half particles. The allowed values of Z component of a spin are plus minus half H cross, which with gyromagnetic value of 2 yields the two values given in equation 7 for mu Z. I again quote equation 7 over here. Mu S is equal to minus E by twice me GS. Now let us consider the results of the experiment finally. The experiment is normally conducted using electrically neutral particles such as silver atoms. This avoids the large deflection in the path of charged particle moving through a magnetic field and allows spin-dependent effects to dominate. Now, if the particle, next point, if the particle moves through a homogeneous magnetic field, then what will happen? The forces exerted on opposite ends of the dipole cancel each other out and the trajectory of the particle is unaffected. However, if the magnetic field is inhomogeneous, then the force on one end of the dipole will be slightly greater than the opposing force on the other end, so that there is a net force which deflects the particle's trajectory. Now, if the particles, let us say, if the particles were classical spinning objects, what one would expect? Then one would expect the distribution of their spin angular momentum vectors to be random and continuous. Each particle would be deflected by an amount proportional to the magnetic moment, its magnetic moment. Now, producing some density distribution on the detector screen. Now, instead, the particles passing through the Stern-Gerlach experiment are deflected either up or down by a specific amount. The results show that particles possess an intrinsic angular momentum that is closely analogous to the angular momentum of a classically spinning object, but that takes only certain quantized values. This is what is to be taken care of. Particles possesses an intrinsic angular momentum that is closely analogous to the angular momentum of a classically spinning object, no doubt, but that takes only certain quantized values here. The experiment confirmed the quantization of electron spin into two orientation, and this was a major contribution to the development of quantum mechanics, in the sense that it established that spin of the electrons did exist. Thank you very much for your kind attention.